Yes. Don't shut up. Yes. All right. So again, one more time. If something, a solid solute, gets dissolved by water, there's something that has to be stronger, and that something has to be down here in orange in the middle. Now, hydration attractions. Now, you don't have to call it an attraction. You can call it a force. But what does the water simply have to do? Pull the compound apart, right? So it's got to separate that bond. Now, and I showed you a picture of the diagram yesterday where they asked you to draw the molecule, check, where they asked you to surround the calcium ion with water molecules. And I beat that into their brains last year, and guess what? That question showed up. So what's the chance of it showing up again next year? Probably nothing. So, but we're still going to beat it into your brain because I need you to understand it. You should know by this point of exactly how these things are set up and designed. So if you have a solid solute, okay, this is what this is. If you want to drop this in, this is a solid solute. And we're putting it with the piranha of life, which is what? Water. So what's going to happen is this water is literally going to eat away at this solid solute. Okay? And so eventually, you're going to have these water molecules attacking it and pulling it away and separating it out. Okay? Do you think this is where concentrations can change? Yes. Okay? So the more solid solute particles you have floating around, the more higher of a concentration that you have. Okay? And so this is how molarity can also be affected. Now, notice one thing in that question yesterday. How many specific water molecules did they say to surround it with? 4. If that ever comes into question and they don't specify, always go with 4. Okay? That is the common number that you see. Always go with 4 water molecules surrounding an ion. Because here's the difference. Is it a 1-to-1 ratio for ion to water? That's the key that I need you to understand. Because it be 1, and so if you look down here at the very bottom, down here, notice, it's not just 1-to-1, right? Because 1 water molecule can't surround this huge ion. How many waters is it? In this case, it's actually 5. But is it engulfing that entire particle? Yes, that's the key that I need you to understand. The second key that I need you to understand, so number 1 is engulf it. Number 2, does the way the water molecule around the ion matter? Yes. This is the negative anion. So what part of the water should be facing? The hydrogen. Why? It's positive. That is the key concept to making sure that you understand these things, okay? So here's another picture. The water molecules separate the sodium chloride ions from solid NaCl. So it's going to dissolve, and notice again, you've got the large chloride anion surrounded by the water with the hydrogens facing it. Then you've got the smaller sodium ions surrounded by water with the oxygen side facing it. Now, why would the oxygens be facing the sodium? The charges are opposite. Oxygen is negative. Is that right? Yeah, oxygen is negative and the sodium is positive. Okay? All right, so again, take a look at this again. Is this drawing correct? Is it correct, though? All right, the sodium is the blue and the chloride is the green. It is correct. Okay, why is it correct? Because the oxygen negative is attached to the blue positive, right? And the negative green is attached to the white hydrogens of the water. So technically, they did this right. Okay, so very good for whoever drew this. Beatrice, the biologist. Good job, biologist. All right, so somebody read me that first sentence.
Water can also dissolve non-ionic substances such as alcohols, sugars, and
Okay, pause there. Non-ionic. First of all, what do we know about ionic substances? They're charged. What about non-ionic substances? They're not charged, but can they be partially charged? Yes. And so above all this somewhere, I can't exactly tell where it says, wherever it says non-ionic, write partial charges. Okay. So if something has a partial charge, can water attach itself to it? Yes, exactly, it can. Some of those things that are partially charged are alcohols and sugars. Do water and alcohol mix? Yes, they do. Otherwise, you wouldn't have alcohol. Okay. Sugars. Does sugar dissolve in water? Yes. If it didn't, then we wouldn't have sweet tea. God bless the South. Okay. So, because of these two polarity factors of these two molecules, you would lose probably the two most popular drinks in the world. Well, I'll take that back. In the South. So because of the polarity aspect of it, this is what you need to know. So now that you know that alcohols and sugars are polar, how do we know they're polar? So I need you to add this somewhere onto this. Like dissolves like. However, is that a very good way to talk about it in AP chemistry terms? No. So what is another way to alter this? Polar dissolves polar. So we know water is what? Polar. So we can also say that water will dissolve, yes, water, but alcohol, do what? Well, it does dissolve itself, doesn't it? If you put water in water, will it dissolve itself? Exactly. Bingo. So it does dissolve itself. Does water dissolve ice? But does it dissolve it? Megan, you think? So here's the next important concept that I need you to understand. This right here. OH bond. What is that? It is hydroxide. You know that. And if you don't, that is not a good thing. So this thing right here, so whenever you have an OH, we know it's hydroxide, but here's the key concept to it, is that this part of the organic molecule, when it is attached, it creates partial polarity. I gotta get a better computer. This thing is just too slow for me. The hydroxides create partial polarity on these molecules. So let's kind of attach it to something else. If sugars and alcohols are partially charged, why do you think they're partially charged? Because they have hydroxides on the end of them. Now, why would a hydroxide create a partial charge? It's more electronegative. Thank you. So if you notice sitting right here, so between carbon and carbon, is either side of this going to win the battle? If there's an electron sitting right here, no. But as soon as you throw this thing in, is there a big difference in electronegativity? Yes, so here you've got an E-neg difference. So what's going to happen is this oxygen is going to pull, let me see if I can do this a little better way. The oxygen is going to pull the electron this way. So when it starts pulling that electron this way, what is this little funky looking S-looking symbol? It's a partial charge, right? So it's partially negative and partially positive. Well, now this little hydrogen's hanging out here, and it's got some negative, it's got some partial ends that are positive to it. So as soon as we drop this thing into water, what's the water going to do? It's going to form an IMF. Okay? It's going to form a force. It's going to form an attraction between those two things. Real quick, let's see how smart some of you are. This has two carbons. What's the prefix? Eth. This is carbon base. So this is eth. Okay? Now you probably won't know the rest of this, but anytime you add a hydroxide to the end, or to a carbon-based substance, it turns into an alcohol. So this is ethanol. Where do we have ethanol? In our gasoline. Is there water in gasoline? Most of it is gasoline. So when you're pouring it into your gas tank, this is actually what you're pouring in there. So let me ask you a question. If you pour sugar in someone's gas tank, is it good or bad? It is really bad. Why? Talking about molecule. What's it going to do? It's going to corrode the tank, but I'm talking about molecularly, not the iron or the steel in the tank. It's going to separate the ethanol and the water from itself, which basically is going to create more issues. And so then you're going to have sugar attaching to the ethanol, right? Because aren't sugars and alcohols both polar? So can they create attractions? Well, if you're dragging sugar through your engine, is that a good or a bad thing? That's a really bad thing. So you've got this macromolecule like sucrose that's going to completely engulf that ethanol, and so when you're putting it through now we all have combustion engines, right? So when it goes through your engine, it can't combust that ethanol, okay, because it can't break those things apart, which will make your engine shut down. So don't put sugar in people's engines. Yeah. I mean, that will lock that thing up. So, but on a chemistry level, the reason why is because this right here, that chemical bond, or excuse me, that chemical attraction is being altered. What's wrong? Okay. I don't know the answer to that question. I know where you're going. I really don't know. It will mess it up. Who did this? I really don't know the answer to that question. Okay? Alright, so, again, the whole reason is because this right here is going to be messed up. That's the whole reason you don't put sugar in gas tanks, is because you're messing that intermolecular force up between the ethanol that's going in your vehicle and the water that's present in the gasoline, is that you're going to mess that part of it up, okay? So, this is when polar dissolves polar. But if like dissolves like, then, excuse me, check. Let's come back over here. If polar dissolves polar, then what else can we say? Non-polar dissolves what? Okay? So, if we have things such as oil, what do we know about oil in terms of its polarity? It's non-polar. So, oil will dissolve an oil. Now, what is another word for an oil? A fat. What's the biological name for a fat? A lipid, okay? So, fats do not dissolve in water. We know that already. But why molecularly? Water's polar and fats are non-polar. That's the reason why it doesn't work. So, like dissolves like is a useful way. So, polar and non-polar, polar and polar, non-polar. Alright, so saturation of solutions. A solution that contains the maximum amount of solute that maybe dissolves is saturated. I need you to add a big, huge word to this right here. This, and again, we're going to get to this, and it will make a lot more sense later. But saturated is, and I don't know where you're going to add it, is at, and this is the first time you're going to hear the word probably millions of times. Equilibrium. When you hear of a solution that is saturated, it is at equilibrium. Now, we need to go ahead and define equilibrium. So if you want to add a page in your notes, that may be a good idea, but I want to go ahead and define it. So before we ever actually start talking about equilibrium, you know what it means. And don't say it's when things are equal. Nothing is changing. You're actually technically right. So here's what it technically is. When the rate of the forward reaction is equal to the rate of the reverse reaction. Notice I did not say the concentrations are the same. Now, we need to actually do one more thing. What is this word? It's a change in something over time. So let's just call it this. What does the brackets stand for? Polarity. That is something you're going to get real familiar with in the next few minutes. The change in concentration over time. Now, What is a forward reaction? Do I need to pause and let y'all get that? Okay. So again, rate is a change in concentration over a change in time. What is a forward reaction? Very, very good. So, reactants converting to products. Do you agree that's the forward? So, logically, over time, what should the concentration of reactants do? Reactants. Why should reactants decrease over time? Because we're converting them, right? So what should the concentration of the products do over time? They should go up. So if our concentration is changing over time, is it changing with a certain amount? At some point, the rate, again, what is the rate? The change of concentration over time. Of the reverse. What is the reverse reaction? Products converting back to the reactants. They must be the same. Now here's the hardest part for students to understand. Do the numbers of the concentrations have to be the same? No. And we're going to get to this a little bit later, but let's pretend that Nick and I are ants. Okay? And Nick starts with 10 rocks, and I start with 5 rocks. Are our concentrations of rocks equal? No. So, but we're going to work like little ants, and Nick's going to try to take my pile, and I'm going to try to take his pile. He's got 10, I've got 5. What if we started taking one rock from each other at a time? So he comes and gets one of mine, and I go back and I get one of his. What is our rate? 1 rock per trip. Are our rates equal? Yes. So would we be at equilibrium? Yes. But would our concentrations ever change? No, because it would be equal exchanges. But what if he came and got 1 and I went and got 2? Are we at equilibrium? No. Would our concentrations eventually change? Yes. Okay? And so when the concentrations are changing, you're no longer at equilibrium. So you're going to have a constant rate in order for your concentrations to remain constant. So when you're at equilibrium, this is true, but here's the last important part. The concentrations are constant. Now, could they be equal? Could they be? Yes. If Nick and I both started with 5 rocks each, and we went 1 for 1, are our concentrations equal? Yes, we had the same amount of rocks. Would our rate be equal? 1 to 1, right? So would we be at equilibrium? Yes. So regardless of the values, 2 things have to happen. The exchange rate must be the same, and the concentrations must become what? Constant. Does that make sense? I promise it'll make more sense later. We'll get into the math, we'll get into it, but we need to define an equilibrium. And where did this come from? It's because when you see this word, every bit of that occurred. It's a little different. That's more of a biological. This is straight solution. Saturated means that there are no more bonds available for carbons, which basically means every carbon has a single bond. Unsaturated means there's a double bond somewhere in the chain that would allow for carbon to create another bond if they broke the double bond. Yes, exactly. Okay. What? Equilibrium is only for saturated. So, if you go to your grandmother's house, and there is the exact amount of sugar that is dissolved in that water where it can hold no more and hold no less, what would you consider that tea? Saturated. So what I'm trying to get you to understand, if that's true, do you agree that that would be sugar dissolving into its particles? But at the same time, somewhere else, what else is happening? The particles are turning back into the molecule. That is equilibrium. And why is that so hard for us to understand? We think that, but that is true. There's something else I'm fishing for. Can you see it? That's the hardest part. Is that we don't understand equilibrium because we can't see it happen. And so that's why we have to kind of figure it out from this perspective. All right, so a solution that contains less solute than saturated solutions is what? Unsaturated. That's easy. A solution that contains more dissolved solute than a saturated solution under the same conditions is considered supersaturated. Out beside the word supersaturated, please write need heat. The only way you can create a supersaturated solution is by making that water dissolve that solid. And when I say that it's an extreme case, it is crazy extreme to be able to see a supersaturated solution. At the end, I'll show you all a little video of some supersaturated solutions. They're kind of hard to create. You got to have the right specific parameters. All right, so solubility. Solubility is defined as the amount of substance that dissolves in a given volume of a solvent at a given temperature. Highlight that, at a given temperature. Can temperature change affect your solubility? Whenever you make tea, what type of water do you use? Why hot? It dissolves faster and more efficiently. Okay? Solubility is temperature dependent. So, heat them up, speed them up. If I run at you at 10 miles an hour or 100 miles an hour, what is going to make more of an impact? 100. What are we trying to do to the molecular compound of that sugar to make it tea? We're trying to smash it, right? Well, if I take a water molecule and I run it into it as fast as I can possibly, is there enough energy transfer to break the bonds to break the molecule? That's the whole purpose we use hot water instead of cold water. Because in cold water, it's moving slower, which doesn't have enough kinetic energy to break the bonds in that sugar. You can, but it's not as efficient. Yes, because when you reduce the pressure enough, the molecules end up moving faster because there's nothing controlling them. So yeah, I mean, that's the whole purpose. If you want to boil water, you don't technically need heat. You just technically need to reduce the pressure on top of it. Okay? All right, so electrolytes versus non-electrolytes. I'm going to go pull out a little demo. I think I did this for y'all last year. I did this for y'all last year for some of you, and I'm going to show you again, and if I have enough time, I'll pull it out. So, pure water versus a sucrose solution versus a sodium chloride solution. So when you notice something, you have pure water. Now, pure water that's liquid. What does that mean? It's just distilled. It's nothing else but just H2O, right? So because the light bulb is not on, what does that tell me about this particular solution? There's no charge. Here's what I need you to understand about electrolytes versus non-electrolytes, and I want you to write it up there at the top, and it has to do with one word. Ions. If you don't have ions, can you conduct electric current? No. That's the whole key. When we get into electrochemistry, that's all we're going to be focusing on, is the ions that are present in the solution. So if it's just pure H2O, are there ions in solution? I'm going to hold that thing for later, because I'm just going to throw this one word at you and we'll talk about it later. I'm not lying to you, I'm just withholding the truth. Auto-ionization, and we'll talk about that later. Okay? Just keep that word in the back of your mind. It's not enough to conduct current, but my question was, in pure water, are there ions? Keep that thought back there. Okay? So, sucrose. What do you notice about this particular solution? There's non-ionic. But here's the hardest part the students don't grasp. Earlier, we talked about, does water dissolve sugar? Yes. But does that create ions? No, that just creates attractions, right? Just because there are attractions does not mean there are ions in solution. So even though that there's going to be a dissolve process going on here, that's just creating more links, right? It has nothing to do with electric current flowing through the solution. Now, when we drop some sodium chloride in there, what are we producing specifically? Ions. Because what is happening to the sodium chloride? You're getting the sodium ion and you're getting the chloride ion, which allow the solution to conduct electric current, right? So that's the only reason that this is going to work. Yes, sir. Say that one more time. You could take a glass, and as long as you have wires that will connect that will complete the circuit, like alligator clips, you can create electric current from salt water. Absolutely, you can. You got a lot of ocean water to pull in. There are actually, you can take salt water, pour it on an apple, and plug your charger into the apple, and it will charge your phone. It won't last very long, but it will work. If you had a constant flow of salt water through the apple, it will work. It'll pull all the ions out of the apple and through the salt water. However, that's not really good for your charger because it will corrode the prongs. But it will work. Yes, sir. Okay? All right. So we've got two metal prongs in here, right? We've got these alligators clipped to complete the circuit. So the whole purpose of electricity and allowing it to flow is by completion of a circuit, right? So you have a point of source of electricity, and it's got to tie all the way through. So what happens is when we pour sodium chloride into the solution, will water destroy the ionic bond? Water is a piranha. So yes, it's going to break that bond. So when you take Na and Cl who are bonded and you separate them, you now have sodium and you now have chloride. But are they ions once they have been separated? Yes. So you have an ion here and an ion here. What causes electric current to flow? If that is in here, will your light bulb work? Yes. Are those ions in that solution? Yes. Therefore, electric current will flow. Okay? Yes, sir. Yeah. All right, so if an ammeter measures a current and the bulb glows and the solution conducts electricity, if the ammeter fails to measure a current, then it does not conduct electric current. All right, an electrolyte. This is what you need to know. An electrolyte is a substance whose aqueous solution conducts electric current. That's the definition. If you said Webster, what's an electrolyte? Solution that conducts electric current. I need you to know not the what it is. I need you to know the how it is and the why it is. So why does it conduct? Yes, ma'am. Yes. Yes. Now, there are some solids that can conduct it, but it's very rare. Okay. So, the more mobile and charged. Highlight those two words. Mobile and charged. What does mobile mean? To move. So if something is stationary, is it going to be very good for current? No. In charged, what is that one simple word that tells us something is charged? Ions. That's what your key. You're looking for something that is an ion. And again, what is an ion? Something that has a plus or minus attached to it. So mobile and charged particles present. The higher the concentration of ions in the solution, the better the conduction. So let me explain this. If I have a 0.1 molar solution of hydrochloric acid, and I have a 1 molar, so 0.1 versus 1, which one has a higher concentration? 1. So which one would be a better electrolytic solution? The 1 molar. So let me explain something to you. So if we come over here and we talk about molarity, what is the formula for molarity? Mole over liter. So if I have a 0.1 versus a 1, how many moles are in how many liters? So I have 0.1 moles in 1 liter. Do you agree? So I have 1 mole in 1 liter. True or false? True. So, what are moles? Nope. That's very good. It's an amount of call it stuff. That's real technical. All that junk. So the more junk, the more stuff you have in the same volume, do you have more ions that can flow? Yes, absolutely. So when we're talking about an acid, there are two things that qualify an acid. What's one of them? Got to have an H plus, and it's got to be aqueous. Those two things must be true. Devin, let me ask you this. What has to be present for electricity to flow? Is that an ion? Does it conduct electricity? That's what it does. You with me? So if I take an acid and I put a contraption to test the conductivity of it, should it glow? Yes. So the higher the concentration, the better conduction. So again, two things. Number one, charged and mobile, ions must be in solution to conduct electric current. Yes, ma'am. Milk is basic. Orange juice. That's a great question. Acids have ions, right? Bases also have ions. So bases will conduct electric current as well. We'll get into all of that. It is, hydroxides are common bases, but not all bases. We're going to talk about the three definitions of bases. The first one was the presence of hydroxide, but they found out that that's not always true, so they had to alternate it. Yes, sir. Sure. Yes, sir. That is a great question. Why would they be in Gatorade? What would be the purpose of them in Gatorade? Do we have electrolytes in our body? Yeah. So once we use those, because if you take an AP Bio, how many of you AP Bio? Sodium potassium pump? Yes. What is it used for? Active transport. Well, so it's going to move large macromolecules across the surface of the cell membrane, right? So those are ions that are in our cell membrane that allow active transport. So basically taking something that you have to require energy to pull. So that's what the electrolytes are used for. So once we have a high level of activity, we have burned up some of those electrolytes. So we need to replace them. Now, something that we talked about last year is Smart Water. They claim on their bottle to have electrolytes in their water. Well, according to our conductivity meter, there wasn't any. Gatorade worked. No, Gatorade worked. Yeah, it was very little, but it did work. So again, it's interesting to see. Now, you probably could. I'm sure there's enough. It's one of those lawyer disclaimer things that it's supposed to have a certain amount, and our conductivity meter is probably not precise or accurate to pick up the small amount that's in there. Yeah. So let me ask you this. No, I'll come back to it. So a non-electrolyte is a substance who does not conduct electricity. So what is missing from solution? Ions. Bingo. So no charged particles. Sugars, alcohols, antifreeze, and starch. And again, I want to stress this. Just because water will dissolve it, does it automatically make it an electrolyte? No, because if it dissolves it, it may just be polar. That's the only reason it will be dissolved. But it still may not produce ions in the end. Okay? Do what? Why? Explain. Why would you have a pool of antifreeze? That will kill them. Why do you have a pool of antifreeze?
Is this like that story about the Red Bull and the coffee? He's just making it up right now. He makes things up. One time
I like the smell of gasoline, but I don't drink it.
he made up a story.
Garrett, shh, Garrett. Okay, so here's the next part. So there's two ways to do this. Number one, we have electrolytes versus non. That tells you what, just in a basic definition, electrolyte versus non-electrolyte. How can you basically define that? if it conducts current or not. Okay? Now, if it is an electrolyte, it has two variations. It's either really good or not as good. So we classify that as strong or weak. Now that we know what an electrolyte is, what has to be present for an electrolyte? Ions. How could we define it as a strong or weak electrolyte? The more ions, we would classify it as strong. So the less ions, we classify it as weak, which is exactly what we have. So here's what you need to know. Strong. Anytime you hear the word strong in this class, you need to know it is referring to the ability of it to dissolve, to ionize, to break apart, to turn into its particles. So, if it is strong, it completely dissociates. If I ask you to dissociate from someone, what does that mean? To get away from them. Okay? So, what is a percentage value that we can apply to the word completely? 100% disassociation. That is a number that I need you to memorize. No, just do it later. Please do it later. So, if it is strong, it is 100%. What if it's 99? It's weak. But it's definite. It is defined as the following. Strong is completely dissociated. Weak is anything but. Yes, sir. No, that determines if it's strong or weak electrolyte. So what we're telling you is there are ions. It does dissolve. But to what degree does it dissolve? So if you want to add that to strong versus weak, it's to the degree what does, or you get what I'm saying there, right? How much dissolves? Is it all or some? It can be up to 99%. So down here where it says weak, somewhere in that frame, 99% or less. But here's the interesting part. Chemistry works in weird ways. It's either 100% or, in most general cases, less than 5. So that's a huge range from 99 to 6, where there seems to be a whole lot of things that just don't reach those numbers. But it's how chemistry works. So here's the next part. We need to go back to strong real quick, because I need you to know the examples of things that will always be defined as strong. So consult solubility rules. Strong acids. So if I ask you what does strong mean? What does strong mean? 100% soluble. It completely dissolves. So if we have strong acids, what does that tell me about the acid itself? It completely dissolves. Strong bases, completely dissolves. Insoluble salts, completely dissolve. I do want to kind of throw this at you. There are 6 strong acids, and I know that's probably hard to see. There are 6 strong acids, and there are 8 strong bases. No, I don't watch scary movies. Why don't you just turn the bucket over? Okay. So let me ask you something real quick. I'm throwing a kink in your stuff. Barium chloride. Write the formula. Ooh, barium chloride. Write the formula. That should be simple for you. Better be simple for you. I hope that it's simple for you. BaCl dose. So, we need to know if this thing is soluble or not. That's going to come with solubility rules, which we'll get to Thursday. So when this thing dissolves, what is it going to dissolve into specifically for this compound? If I wrote that, am I right or wrong? Somebody better say I'm wrong. Why am I wrong? 2 Cl minuses. Because for every 1 barium chloride, how many bariums do I have? Barium, I have 1. How many chlorides do I have? 2. So, is this adding an extra ion in the solution formula? Yeah. So this will dissolve into this, and so we need to make sure we understand how that works. So barium chloride is an ionic salt that completely ionizes. Hydrochloric acid is a strong acid that dissolves 100% into barium ions and hydrogen ions and chloride ions in water, while sodium hydroxide is a strong base. So what will it ionize into? Sodium and hydroxide. Okay? So all three release mobile. What does mobile mean? Moving. Charge. What's another way to say charged? Ions. Particles that are readily conducting electric current. So common strong acids. I'm going to go ahead and tell you this. You have to have these memorized. HCl, HBr, HI, HNO3, H2SO4, and HClO4. Hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric. Those are your 6 strong acids that you have to have memorized. Diprotic sulfate. It is a diprotic acid, but it's just sulfuric acid. Okay? Common strong bases are oxides and hydroxides of group 1 and 2A metals. And we'll talk about those in a few minutes. Yes, but there's 8 of them. We'll talk about those later. Okay? Yes, sir. Come in. It does. It does. Sulfuric is the only diprotic because it has 2 hydrogens. Now, notice what it says. It says, loses its first H plus easily, exists mainly as H plus and hydrogen sulfate ions in water. That is true, and we'll get into that at the very end of the year when we talk about acids and bases. All right, so we do not dissociate completely. I would highlight this part right here at the bottom. Pick this color. Only about 5% dissociation. The weak acid, acetic acid, and the weak base, ammonia, are pictured below. So let's look at those real quick. Oh, actually, this is something else. This right here, and if you want to label it like this is a solid. How do I know this is a solid? Look right there. It tells you it's a solid. And it says BaCl2 dissolves. Is there any solid left? What are all of those? 100% ions, right? So would we consider this strong or weak? It is considered strong. And for what reason and what reason only? 100%. Okay? What about that HCl? Do you have any solid left? Okay, go ahead, Bat. Yeah, because they're not stuck together. See how they're all stuck together here? Okay. Over here, strong or weak? Why strong? Because there's all ions. And this is hydrochloric acid. This is sodium hydroxide. This is a strong acid. This is a strong base. SA stands for what? Strong acid. SB stands for strong base. What do you think WA is? Weak acid. WB. Weak base. Very good. So is this strong or weak? Strong, because it's 100% dissociation. Okay? Now, down here, I'm trying to remember what these pictures are, because I don't remember. I think this is sugar right here. Very good. Thank you. Thank you. That was very good. So this is what this is. This is NH3. All right, I'm actually going to come out here. Let's call it 98% NH3, 1% NH4 plus, and 1% OH minus. Now, obviously those numbers are maybe a little off, but I'm doing them by parts. But my question is, will it still conduct electricity? Why? What has to be present for a conduction of electricity. Are there any ions present? Yes. So even though it has ions, it can conduct electricity, right? Because these two are ions. How do we know those are ions? Because they've got pluses and minuses on them. But is this a strong or a weak electrolyte, and why? It's weak. Why is it weak? It's not 100%. Devin, does that make sense? Hang on one second. Devin? Say it again. Do you see a plus or a minus? No, so it's not. It's a neutral molecule. That makes sense? Okay, over here. What is that? This is sugar. Do you see any ions? There's one little something or another right there, and I don't really know what that is. Is that a hydrogen? All right, so it's like 1H plus. So technically, is there an ion present? Yes, but would it do very much conduction? Very, very, very little, right? So even though there's that one, technically there's an ion present, but it's really not going to be enough to make a big deal about it. Any questions on that? Okay. All right, aqueous solutions. What ions and how many each are formed when KBr dissolves in water? Okay, K plus and Br minus, right? So you've got K plus and Br minus will dissolve with water into K plus and Br minus. True or false? True. What and how many of each one of those? Okay, you've got 2 nitrates and 1 barium. So, does this make sense? You've got 2 pluses, so how many negatives do you need? 2 negatives, which is why you have the nitrate right there. So when it dissolves, you've got a barium left, and you've got 2 nitrates left. Do these pictures make a little bit more sense? Okay? Electrolytes. So here's what I want you to do on this, and I think it was in the video, but if you have it pulled up on your iPad, just put a Y or an N if it is an electrolyte or it is not an electrolyte. Pure water. No, but I'm going to do this. I'm going to put an asterisk beside this. But I remember that big ugly word that I wrote down earlier? Auto ionization. We'll talk about that later. Tap water. Yes. Why? It's got all those little minerals floating around in it. Sugar solution. No, it should not. Sodium chloride solution. Yes, absolutely. Hydrochloric acid. Yes, but let me ask you. Strong or weak? Strong. Hydrochloric acid is a strong acid, it's a strong electrolyte. Lactic acid. First of all, where do you get lactic acid? Your muscles from fatigue, right? Are all acids electrolytes? Yes. All acids and bases are electrolytes. The difference is it strong or is it weak? So yes. Ethyl alcohol. No. Alcohols do not. Impure solid sodium chloride. No, it will not as well. But what if you take that sodium chloride and pour water in it? What if you turn it into molten sodium chloride? And here's what a molten is. It is solid substances who have been melted into pure liquid sodium chloride. That's a good question. Say it one more time. Very good. It has changed states of matter, but has it changed compounds? No, that's a physical change. Very good, Colby. Yes, sir. They cannot be. They're dissolved in water, but they're not ionized by water. They're what? Classified as what? Yeah, that's what a molten solid. It cannot, because it's a physical change, and you're not separating into its ions. You're basically, You're increasing the temperature so much that you're melting the solid form of it into a liquid form. You have to literally take the Na and the Cl and pull them up. Exactly. Exactly.